So I am now working on chapter 11. So let's see, chapter 11. So once we're done with chapter 11, we're going to be moving on to chapter 12, right? So I worked with Jacob yesterday. Ignore the email I sent since you guys are already here. Just a reminder, for those who have probably forgotten. Okay. I worked with Jacob yesterday to record the session all the way to this page right here. So he was asking me some homework specific questions. I already posted that recording late at night yesterday. So feel free to go ahead and watch that to kind of bridge the gap between where we left off on Tuesday and where we're picking up today. Okay. So my goal is to complete this chapter today and to work through all of chapter 12. So I left, I guess, the best for last, phase diagram. So if you are not done with the lab from Sunday, the one that was due on Sunday, after this video, after watching this video, please make sure you work on it to get caught up. It wouldn't take me that long to go through chapter 12. So once I'm done with that too, which is today, that's the goal, is to get done today, then you should be able to go ahead and work on that too. I just realized I'm not sharing my screen. I have to go through like so many checkpoints, share my screen. Okay. I am recording though. Can you all hear me well? Okay. It just looked like somehow maybe the quality on my end was low, but okay. Looks good. Once again, if you have any questions, please feel free to either speak up or just say it in the chat box or message box. Okay. So after looking at the intermolecular forces and seeing how temperature can weaken the intermolecular force, because remember, when you're reading through the dialogue in chemistry, you're seeing all these words like the molecules are trying to escape when we go from liquid to the gas phase in order to make a gas, especially in this context, right? We're not just talking about the gas, we're talking about the vapor. Vapors are essentially escaped liquids. They're former liquid molecules that got to escape, right? So vapors are escaped liquid molecules. That's kind of where they started off from. So in order to make a vapor, the molecule has to gain enough energy to escape, right? And that allows us to go from one phase or one state to another, from liquid to gas. Same thing with solid to liquid. In order for the solid to form a liquid, same thing has to happen. There has to be some escaping, right? And essentially, in this case, you go from molecules that have a very strong and tight intermolecular force to molecules that now have weaker intermolecular forces. So in this case, going from solid to liquids, the molecules do not escape completely. They do escape the strong intermolecular force, and they end up kind of close to each other, relatively close. But this time, the intermolecular forces that are forcing the molecules close to each other are much weaker. We're going to be stepping back and looking at the relationship between liquids and gases, solids and liquids, solids and gases from a more macro level, from a more holistic level. We saw yesterday or in the other video that the molecules in solids can also escape to form gases. Okay? And remember, all of these phase changes are possible with temperature change. But we're going to see that there's more to the picture. Okay, so let me try to show this in a more big picture form, which is you go from solid to liquid, from liquid to gas, and sometimes from solid directly to gas. Remember, you can accomplish the solid to liquid, liquid to gas by increasing temperature, but we'll see in this case, in the picture, the phase diagram, temperature isn't the only factor that influences the transformation. We also have temperature and pressure. Okay. So when you decrease pressure, increase temperature, you can go from the left to the right. In this case here, also increasing temperature. Okay, let me move right to it. Phase diagrams describe the different states, talking about the phases, right? Liquid, solid, gas. End state changes that occur at various temperature slash pressure conditions. So the pressure and the temperature are two factors that can allow us to go from one state to the other. So in this big diagram, we're going to be seeing different regions, and the regions represent the states, right? States meaning, let me start with solid, liquid, and gas. I don't know why I'm doing it randomly like that. And then to separate the phase changes or to separate the states, we'll have lines. And we're told here the lines represent the state changes. When we have the lines dividing one state to another, on that line we'll have the transformation from one state to another. So you have things like boiling or freezing or melting, okay? So it all depends on what that line is separating. Is it separating liquid gas? Is it separating solid liquid? So the liquid gas line is called the vapor pressure curve. Now here they're using thermodynamic terms. In the background information, you have different group of chemists. Now chemistry is a big field in science where there are different groups that specialize on different areas in chemistry. And the ones who specialize in thermodynamics get to name the area they're focusing on. So we have what is called the vapor pressure curve. This is the line that separates liquid and gas. And remember, the vaporization usually refers to liquid becoming a gas. So if you memorize poorly like I do, then the words have to have meaning to help you kind of remember, which for me, you form a vapor when a liquid becomes a gas. So the vapor pressure curve only goes with the liquid gas barrier. Okay, so on that line, the liquid gas barrier, both phases exist in equilibrium simultaneously. Okay, so let me go to the picture so you can see it. In this picture right here, they're showing you the vapor pressure curve or vaporization curve. Remember, vaporization is all about the formation of vapor. You're trying to make a vapor, right? We usually make vapors from liquids. So you can see here in this graph, in this picture, we're separating the liquid phase. I just put the L here for liquid phase from the gas phase. So what they're saying is, if you're actually anywhere on this line that I drew, this hard line here, you don't just have a liquid or a gas, you have both phases existing. When I was learning this, it kind of reminded me of neighborhoods, or maybe not neighborhoods, but countries. If you go to the border of a country, like if this is one country, so I'll call this country 1 versus country 2, and you go to the border of the country, for the most part, at the border, the cultures mix. You don't see just the culture of one country or the culture of the other. Usually at the border, you kind of see a mix, a hybrid of both, cultures. So it's something like that where if you are in this region right here, you only see liquid. If in the region right here, you only see gas. But on the border of both phases, you see both physical states, and they both exist. So one does not cancel out the other. They both exist. So they call that equilibrium. So like equal representation from both sides. Okay. So equal representation, or the equally present. Oh, I'm running out of space. Okay. So let's say equally present. Keep it simple. Equally present. Okay, I barely wrote that. So on that border of the liquid region and the gas region, we have both liquid phase and the gas phase, right? Okay. So the same thing happens with this other border here. Let me use a different color just because, I have all these colors and I'm always using the red one, right? So now we have the border of solid and liquid, which I think is appropriate because when you're going from liquid to solid, you're actually freezing, right? So from liquid to solid, now we have the blue border. If you're in this region right here, all you have is solid only. If you're in the region to the right, all you have is liquid only. But when you look at the border, once again, you have both phases because both are equally present and they're equally represented. So here, once again, you have equally present phases, right? So you will see both solid and liquid if you run through these conditions. So I'm going to step back and talk about what the conditions are. And then I guess I'll use the green color for this last part. Sure, green color. In this last part here, this curve separates the solid from the gas. Okay. Oh, I forgot to mention, in the blue region, this is called the fusion curve. Remember we mentioned this before, the delta H of fusion. Fusion in the thermodynamic world just means either melting or freezing. Okay. So let me write this somewhere. In the world of thermodynamics, remember these are the group of chemists who major in this section, so they get to be the ones that name this. Vaporization. This term here tends to be used to refer to boiling, right? And boiling just means you're going from a liquid to a gas, okay? And then we have the term fusion, and fusion tends to go with melting, and that's going from a solid to a liquid, right? And then we finally have sublimation, and sublimation refers to sublimation. You're going from subliming, right? You're going from a solid to directly to a gas without ever forming a liquid. Okay, so you want to be aware of those terminology. When they talk about one, they mean the other, vice versa. So sublimation curve, once again, any point on this curve, you will see both phases, but if you go to the left of the curve, you see a solid, right of the curve, you see a gas. Okay, and then where the three different borders meet, right here, just like, remember, in the borders, you have the mix of cultures. In the borders, you have the mix of phases. So where the three borders meet, guess what you have? All three phases. Ergo, the name triple point. In the triple point, you have all three phases. Okay? So triple point, you have all three phases, solid, liquid, and gas existing. Okay? So now let me step back a little bit and look at what the phase diagram shows us. Besides showing us the borders in which the phases kind of coexist in equilibrium, we're seeing a graph, right? And in every graph, you have the label for the y-axis and the x-axis. The y-axis here is showing us the pressure. So we're being told, for us to really see these phases, you have two important factors that get to control these phases. One of them is pressure. The other one is temperature. Okay, I mentioned this yesterday. When somebody asks you what is the boiling point of water, we usually just give the temperature. We never give the pressure. So somewhere in that conversation, the pressure is implied or it's ignored. So what I'll do this time here is erase all these marks I have on the picture to describe this. This is actually the phase diagram of water. So we're going to be talking about water. In regular phase diagrams, which you will see in your lab work if you've been working on it, in regular phase diagrams, this fusion curve right here is actually leaning forward a little bit. It doesn't lean back, right? But water is that unique molecule whose fusion curve leans back. So this is one of your questions in your lab, and I'm going to go ahead and address that right now. Okay. Why does the fusion curve for water lean back versus leaning forward like the other chemicals? Well, water has that unique property, right? Remember, this chapter was all about intermolecular forces. So the water molecule, right here, Lewis structure, has the unique ability of having two hydrogen bonds. Not just one, but two hydrogen bonding capacity. For that reason, water having the hydrogen bond, when the water molecule solidifies, it actually forms a hexagonal arrangement in the solid. So you have water molecules. It's hard for me to draw this, y'all. Let's see. H, O. Yeah, it kind of works like that. I'm really trying to draw this. I don't think this looks very hexagonal, but you get the idea. In the end, when these are arranged, it actually looks more like a hexagon. The spaces between the molecule looks more like a hexagon. Because of that, you actually have a lot of air trapped in the molecules of water. You know what? I have the internet right here. Let me see if I can find a picture. I was doing metric prefixes in my other class earlier before you guys. Let me do frozen, if I can spell frozen, frozen water molecules. What is frozen water pipes? Okay, let's see. There it is. You see, I could draw it horribly, or I could just look at it here. So we go from liquid water, right? Hopefully you can see this picture, to frozen water. With other physical states, the liquid version of the chemical, you have the molecule somewhat spaced, but then when you go to the hard or the solid version of the molecule, they're tightly packed. But in frozen water, the molecules are not tightly packed. I mean, they are as tightly packed as they can be, but there's all this space between them which has air trapped in there. What does that do to the structure of water? It actually makes water, solid water, less dense. So the fusion curve drops backwards to communicate solid water, which is ice, is actually less dense than liquid water. Okay? So that's why this slopes backward. If you have the phase diagram for something like carbon dioxide or alcohol, this will actually slope forward. And so another thing I want to show you is I have to be careful with the internet. Alcohol ice. So I'll say frozen alcohol. Okay. Alcohol cube. No, yeah, I'm usually scared of showing stuff on the internet because I'm like, I have no idea what I'm going to be seeing out here. This is not really helping me at all, but if you see the scientific version of this, when you have a frozen alcohol cube, it actually drops right to the bottom. What they have here is ice cubes and alcohol drink. That wasn't my goal, y'all. Anyway, if you're able to see a frozen alcohol cube, it drops to the bottom because the way the molecules pack is very dense, okay? So that right there is a tidbit for your lab portion. Anyway, so we're being told here as we look at this diagram, you want to get the pressure and the temperature combo that allows a specific physical state to manifest or to actually be seen, right? So we're told here on our graph, we have a critical point, and this is the furthest point on the vapor pressure curve. In the critical point, right here, the critical point is a pressure temperature combination for water in this case here, where somehow there is no barrier between the phases. What this means is if you can get your water to a temperature of above, I don't know what this temperature is because they told you right here is not to scale, right? So you can't just estimate its actual value because it's not to scale. But if you can get whatever the temperature is right here, let's pretend, I don't know what the actual value is. Let's pretend it's 500 degrees Celsius. And then the pressure here, 1000 torr, because it says also not to scale, so I can pick whatever numbers I want. Let's say you got liquid water to a temperature of 500 degrees Celsius, a pressure of 1000 torr, which is the critical point. You will get what is called a supercritical fluid. You see in this corner here, there is no barrier, there's no separation between liquid and gas. That means you will get a weird phase of water where you have both liquid and gas, but they are completely mixed together where you can't tell one from the other. That's what critical point is. We're getting beyond that critical point. Okay, so critical point is a temperature and pressure combination where the liquid and gas phase are indistinguishable. Oh, I'm doing much better with spelling right now. I wasn't doing so well this morning. It was too early, right? The liquid and the gas phase are indistinguishable. You can't tell the difference. How do I know that? There is no barrier. The barrier means difference. Okay. So what we're seeing here is the pressure and temperature combinations that allow a certain phase to exist. Let me move this a little bit out of the way. Let's look at this chart, and from this chart, let's decide certain things. I want to look at this chart and figure out at what pressure is the boiling point. So now I mentioned this was a vaporization curve, right? This is also the boiling point of water. So even though we think the boiling point of water is just one temperature, 100 degrees Celsius, all these are the boiling points of water. Imagine going out there and telling your friends, apparently there's so many boiling points of water. They'll be like, okay, we probably don't care or whatever, right? So we have all these boiling points of water. There isn't just one, but the one that we tend to communicate is this one here, right? Water boils at 100 degrees Celsius. Okay, that's only partially true, but what's the pressure that goes with that number? And the pressure of 760 torr, which is the same thing as 1 atmosphere. Okay, so water boils at 100 degrees Celsius if the pressure is 760 torr. So what I can do here, like I was explaining yesterday, is I could lower the pressure and say, well, what if water is at a pressure of, let's say this is 650. What temp, yeah, 650 torr. What temperature will water boil at? What do you guys think? Oh, I was told not to complete a sentence with the preposition. What will be the temperature at which water will boil?
90 or 80.
Yeah, something less. I'm just laughing because my husband was like, that's a preposition. I'm like, okay, sir. Yes, sir. I know English is not my first language. Yeah, 90 or 80, just estimate something. Hey, Jacob. Okay. So let's see. Now, since we know how to read this, once again, it's estimated, right? Since we know how to read this, what do you all think is the triple point of water? So give both the temperature and the pressure. What's the triple point of water where all three phases exist? Let me zoom it in so you can see. Of course, you're estimating it, right? If you tell me 1,000 torr, I can tell you real quick that's wrong. But whatever number you give me, I'll probably say it's right. If it's not 1,000, if it's less than 1,000, probably say it's right. So for the triple point, what do you think the temperature is?
Temperature is going to be 0.
At zero? See how this dotted line here is zero. It's a little bit to the right of zero. So it's not exactly at zero, but it's to the right of zero. So what do you think?
10, maybe.
Okay, sure. I mean, I can't say anything, but yeah. So you see how the zero is to the left of the point? Maybe I made the point too big, but you see? Yeah, so 10 works, 10 degrees Celsius. What about the pressure?
Maybe about 650.
Sure, I'll take that. Yeah. So you can estimate the triple point of water to be about 10 degrees Celsius and then 650 torr. Okay? So you're mostly really reading the graph. So if you have so many boiling points, you have so many melting points, different number for different pressure. And then you have so many sublimation points. Okay? But they usually just have one triple point because all those three have to meet. So let's move on. I feel like I've kind of over explained this point already. Moving on right here. So we're going to be we're going to be navigating with a phase diagram, going from one point to the other. So the question, I guess, is down here. We're looking at phase diagrams of iodine and carbon dioxide. I told you guys earlier, right? You see how the fusion curve slants forward for these two? Because their solids don't have strong hydrogen bonding capacity, so that's why it leans forward. That means since it leans forward, solid phase is more dense than liquid. So if you get solid carbon dioxide and you put it in the liquid, the solid will fall straight to the bottom versus water where it floats, right? And makes for cool drinks. Okay, so let's see what the actual question is right here. Oh, navigation here. What state transitions occur when a sample of carbon dioxide at negative 60 degrees Celsius and 10 atmospheric pressure is warmed to 30 degrees? I need to write this down. So we're starting with negative 60 temperature, right? And we're going to 30 degrees Celsius temperature, but the atmosphere pressure remains at 10 atmosphere. So negative 60 to 30, but then the atmosphere is at 10 atmospheres. Okay. Oh, I guess they work it out for you here. Do they? Yeah. This is a picture right here showing you what's going on. So you get the phase diagram for carbon dioxide. Yeah, it is that. And then you find where negative 60 is. It's going to be somewhere before negative 56.7, right? And then you kind of estimate what the pressure of 10 atmospheres is, somewhere above 5.1 atmospheres. You're estimating it. Your answer will be the same either way. Even if you estimate a little bit lower or a little bit higher, it will still work, right? You're going from negative 60 to 30. So even if you estimate it a little lower, if you're concerned about estimating, your answer will still work. You see that? They want to know what phase changes you have, what transitions, right? So when you go from here to here, from solid to liquid, what's that transition called? When a solid becomes a liquid, how do we describe that? Or what name do we provide for
Fusion?
solid becoming?
Isn't it fusion?
Oh, you want to be technical. Okay, we can do fusion, or you can just say melting, right? So you can say fusion or melting. Okay, either one works. What about from liquid? The second one, from liquid to gas. What do we call that?
Vapor.
Okay, I see. Vaporization, or you can call that boiling. So on the exam, your exam will be multiple choice. So find the word that fits. Simple as that, right? If it's in your homework and you have to type your answer in, write one. If it doesn't work, write the other. It's one of the two. Okay? Any questions about this? So let's see what they say. Draw the line, we did that. What's all this space? Did they actually answer the question? Something happened, but yeah, melting or boiling. And so you essentially just have that one problem in this one here. Now, in your homework, not homework, I'm calling it homework because you're doing it, but yeah, in your lab work, does anybody have any questions about the phase diagram lab? It pretty much has you, it asks you a bunch of questions about if you have this pressure, this temperature combo, what physical state do you have? Can you drink this? You don't drink chemicals that you're working with in the lab anyway, so most likely your answer is no to that, But the purpose of the second lab is for you to get experience on how to use this, right? This table and how to read it. Does anybody have any questions? I feel like a slide is missing here. I have to find that slide. But yeah, essentially you have melting and then you have boiling. Okay. If we don't have any other questions, I actually already downloaded the other slide. So I have this here. This slide here helps us to answer the questions that are coming up in this weekend's lab, right? Where we're talking about crystalline solids and then modern materials. So chapter 11 had us talking about mostly liquids. We talked about gases a little bit, right? But it was mostly focusing on liquids and the kind of intermolecular forces we see in liquids. Yeah, we discussed gases a little bit and essentially said gases don't have a lot of intermolecular forces. So gases aren't that relevant in the previous chapter. Now we talked about the phase change, and that was important, right? But then we talked about solids a little bit and said that solids have the greatest intermolecular forces. So relatively, solids will have the highest, liquids in between, and then we had gases. Okay. Chapter 12 now focuses on solids. Now with solids, if you compare what I'm covering with the, oh, sorry, I just remembered. I'm sorry. I like to record, to do the recording separately. So let me stop